protocol analysis, signature detection, anomaly detection, this kind of thing. Okay, so let's go back a bit and talk about antivirus. Recall that we were talking about things like worms and viruses and zero-day attacks and exploits and things like this. Yep, that's fine. Now, antivirus is actually not that complicated, right? I don't have an antivirus on my machine except for the one that Windows installs by default, which as far as I can tell is okay. I mean, I'm not willing to slow my computer down with Norton sufficiently, so I don't think it's big enough of a risk. Right? Plus, I suppose I'm trained in some ways not to click yes to things that pop up. Right? My recommendation to family members who ask me whether they should get an antivirus is that they probably should, because I think those family members might click yes when they're presented with a pop-up. Right? So it's a level of personal risk you're willing to take on. But to be honest, I think the Windows one does fine. Now, there are kind of a few types. Antiviruses obviously get quite complicated. But broadly speaking, we can split them into these kind of two major categories, right? Of course, most antiviruses will do both of these things. So the first is signature-based detection. This is the idea of trying to find some kind of fingerprint for a file that represents it, such that we can find it again very, very quickly if it turns up again on a machine. Right? So you want to be able to take a virus in the wild, bring it into your lab, work out what its fingerprint is, and distribute that fingerprint to a database of all the antivirus that you own that's installed on all the customers' PCs, and then when that virus lands on their machine, that antivirus immediately notices it and quarantines it, prevents it from running, even deletes it from the machine. So a very naive implementation of this, let's say we're going to start off with a very sort of naive implementation, would be to just hash it, right? Hash the executable, take that hash and stick it in a database, and then perform some kind of fast hash lookup and see if we've seen that virus before. Now that will work a little bit, in the sense that it will find if that virus turns up again on another machine, right? But as you know, hash functions are pseudo-random, and they have this kind of avalanche effect where small changes in the input lead to big changes in the output. So if your virus changes even a little bit, it will be completely different in terms of a hash, and essentially it won't get noticed. Right? So signature-based detection is usually done a little bit more complicated than this. What we're going to try and do is distill our executable or our virus into some kind of small fingerprint that represents some small code segment of it, something that it does that's sort of quintessential to that virus, so that we can recognize it when it turns up again. And that way, if some other guy binary edits a bit of it and changes it around, it'll still be detected. Right? That's the idea. And you've also got to consider, this has got to be seriously quick. Right? If you've got a virus database of 40,000 viruses and a file comes in, how long do you think a user is going to happily wait before they want to execute that file that they've just downloaded? Right? A second? 2 seconds? Right? That's how long you have to compare the signatures in 40,000 of your database entries. And 40,000 is an underestimate, by the way. Right? So these signatures can't just be, bytes 100 to 500 in this file, this. Right, because that's too much bigger comparison. Right? It's going to take too long. So what you have to do is have these very generic signatures that are very, very lightweight. So for example, if you see bytes 3 and 7 are this, then check byte 8. And if it's this, then check byte 21. And if it's that, we've got a virus. Right? As opposed to just check this large bit for a big virus. Hey, obviously, bigger files will take a little bit longer. You can imagine that viruses might appear dotted throughout a bigger file, like in a zip, or something like that, where there's non-virus material either side. So this gets quite complicated. Now, the good part about signature detection is that it is quite fast, right? If you program this well, it can be done quite fast. The bad news is that if you see a new virus, you'll never ever find it with signature detection because the signature isn't in the database, right? It will always spot known targets, and it will always miss unknown targets, is the way I look at it, right? So zero-day exploits, big problem for signature-based detection. Right? Because unless that 0 day happens to look suspiciously like a previous one, you're not going to find it, right? Which is most of the time. So this is where heuristics come in. Instead of thinking about the actual bytes in a file, can we try and work out what it is that the virus does and sort of have a suspicious level that we kind of increase as it does suspicious things, and then we flag it as, hang on a minute, okay, that is quite suspicious. This could be a virus. Right? So we're going to be running we have to run this program to see what it does. So we run it in a small sandbox or a small VM. We have a look at what it does, operating system calls, opening temporary files, writing to the registry, connecting on a network output. all these things, and any time it does something that looks a little bit suspicious, we raise our sort of temperature, right? And then we get to a level where we say, right, okay, at this point, it's done enough suspicious things that we think it's a virus, right? So this works quite well. This could find a zero-day exploit, because theoretically a zero-day exploit could also do many of the other similar things to a normal virus, write itself into the registry to boot on startup, for example, right? Or write to the Windows System 32 folder. You know, you get the idea. So heuristics are much better than signature detection in some sense. Obviously, it takes a little bit of time to run these things and see what they do. But there's a case of a kind of a trade-off where you set your threshold. If I set my threshold very, very lax, right up here, then no virus will ever reach that point and be flagged, right? So you're going to get a lot of false negatives. That is to say, viruses that were viruses, but we didn't notice them, right? So maybe on the other hand, I want to be a bit paranoid, and I set my threshold really low. So if it does even a little bit of suspicious stuff, we're going to flag it as a virus, right? And if you do that, of course, what's going to happen is you flag everything as a virus. Right, I send you a Word document, it's a virus. Right, email, it's a virus. And you never get anything done. Right? So the way you design this and the way you set your threshold is not easy to do. There's an interesting website called AV Comparatives that does a yearly benchmark of the false positive and false negative rates for lots of different antivirus vendors. Right? I thought it was interesting. Have a look. Right? So at a more complex level, we can replace these heuristics with a kind of machine learning approach. I'm not talking about machine learning very much, because obviously this is not that module. However, it's simply a case of trying to learn a mapping between what it is that a program's doing or the way it's structured and a kind of warning system, right? And so it's just easier, maybe, to train a machine learning algorithm to do this without being explicitly programmed, rather than it is for us to go, right, if this, then this, else this, all the time for all the different virus combinations, which gets very, very difficult. Okay, so that was antiviruses. Now I'm going to segue, I'm going to U-turn completely into... Sorry, do you have a question?
I've got a quick question.
Yeah?
Is this being applied to antiviruses now, machine learning algorithms?
Yes, a bit, but they wouldn't tell you how it works. Yeah, so my experience with machine learning algorithms is they have a lot of false positives, so you have to be very careful with this exact problem with the threshold, right? But yeah, theoretically, yes. To be honest, heuristics work pretty well, so maybe just use them, you know. Right. But if you're trying to sell an antivirus, having it powered by AI is, of course, a nice selling point as well, whether or not it works. Okay, so let's transition completely into intrusion detection systems, right? Which actually do, in fairness, work quite in a similar way to antivirus. It's just obviously about networks and about operations on a computer rather than bytes and operations of an executable. So remember that firewalls don't protect against any attack using a valid protocol. So this firewall here, for example, might have SSH open because this one needs it, right? And if that happens, then it's not going to protect against a buffer overflow in SSH, right, which used to exist, because it'll just go straight through, right? So that's no good. So firewalls don't, that's not what they're for, they don't protect against that, right? They don't protect against insider attacks. If I get access to this machine as an attacker, and I use it to launch an attack against this file server, this firewall will do nothing because it's not there, right? Maybe if there's a host-based firewall here, we might have some luck, but maybe not, right? So intrusion detection systems are kind of like a firewall, but now we're talking about trying to log and disrupt intrusion attempts, right? So it's going to be much less based on just static rules and much more based on the kind of actions that are being taken on the network, what kind of traffic is normal, what isn't normal. And this isn't easy to do, right? So these are still a work in progress. You'll find that you can download and install intrusion detection systems and they will work okay, right? But they'll miss a lot of things as well. And you just end up with swathes and swathes of log files that you maybe decide not to bother going through, and then you've achieved nothing. However, they do get used. There is an intrusion detection system, for example, on the Nottingham network, but I asked and they wouldn't tell me what it is or where it is. So I was unable to test it further, which is probably why they didn't tell me. So, there is a difference between intrusion detection and intrusion prevention, right? Because obviously, so an intrusion detection system is one that's going to detect possible intrusions. Always going to be possible intrusions. We can't tell for absolutely sure, really, right? Unless it's like a signature of a virus or something like this, right? And then it's going to generate alerts and logs for administrators. Now, this is quite common. right? It doesn't really hurt you as an administrator to have something like this running on your network that maybe tries to alert you to someone who may be doing something a bit odd. Right? And then we've got intrusion prevention systems, which are exactly the same, except they also try and stop the attack, let's say by communicating with a firewall and closing off IPs or ports. Right? Now, it struck me when I read this as sort of like, what's the point of an IDS when an intrusion prevention system is just better? Right? Well, actually, intrusion detection systems are much more common because false positives become a real problem if you're just blocking people off a network. If I go into the lab to check my email and then that's accidentally flagged as some kind of intrusion attempt and I get kicked off, I can't get my work done. Right? And by the time I've wasted a huge amount of admin time going up there and asking, it would have been better if they'd just been logged and then they could look later and go, yeah, it's probably fine, or we should follow up on this. Right? So actually you'll find that although intrusion prevention systems do exist, but it's actually quite common just to use detection. Log it, have a look later. Right. And so I'm going to kind of talk about them both interchangeably. Think about an intrusion detection system as something that could have a preventative part to it, right? And we'll just leave it at that. I'm not too worried about the distinction between them. So we could have, just like firewalls, we could have a host-based, or HIDS, or a network-based, or NIDS. That's the last time I'm going to use those two acronyms. So a host-based obviously is going to monitor a single host, and then this is going to be actually on the host, looking at things that they're doing. So app usage, resource monitors, how much RAM's being used, what internet traffic is being used, things like this. But it's going to be specific to a single machine, right? Maybe it looks a little bit at the local network segment, but probably not. A network-based IDS, which you can imagine is much more common sort of enterprise-level networks, is going to monitor network traffic, analyse packets coming across firewalls and things like this, between different subnets, into and out of the university, and stuff like this. Obviously, again, where you put this is going to have a big effect on exactly what it can see and what it can stop or detect. Right, so that's something to bear in mind. Right, so, now, host-based IDS is not that common in that we don't, generally speaking, no one goes around saying, have you got your antivirus installed? Have you got your intrusion detection system installed? Right, no one asks that. Actually, most modern antiviruses have some aspect of intrusion detection built in. Right? They usually call it something fancy. If you look at the list of things that they do, you'll find that one of them is an IDS. It's just got a fancy name. And this is just going to be an additional layer of security that maybe might catch something slightly odd. Right? If an antivirus can't find a zero-day attack, maybe it acts in a suspicious way, or they get access to your machine and that acts in a suspicious way, and then we can detect it. Right? Maybe. Okay? I mean, I think that the computational overhead to run this on your laptop is probably not worth it compared to just running backups and not worrying about it. But that's just me. So what we want to try and do is create a profile of usage for a specific user, right, which probably is different for each user, and then try and build up an idea of what is normal, and then when something deviates from that normal, maybe start logging or disrupting what they're doing. Right, that's the idea. Now, I mean, we'll talk about what is normal later, hopefully in the context of security, and it's difficult to answer, right, because it changes every day. One day I'm running a certain application, then I decide I'm not going to use that application anymore, and I uninstall it, and now my usage pattern has changed. So, you know, this changes all the time. But a host base will have access to things like the CPU, the memory use, application and network stack, things like this. So it will have quite a lot of low-level information, theoretically, on what you're up to. As I said, the network-based IDS is going to depend on where it's put, right? So, for example, if you put a network-based IDS here, then what you're doing is you've got traffic coming from this subnet and this firewall or router to the external network or some other network or the internet or something like this. If you put it here, you're going to be monitoring only the local traffic, right? So maybe me communicating with this server, or maybe the router communicating with us, right? Don't forget that in networking, it's common for your network card to only see packets on the local network segment, essentially as far as the next switch, not any further than that. Right? Otherwise, it'd just be too many packets. So, if you put it in here, you're only going to see traffic in here, right? Which is okay. So it means you have to put them in different places and have multiple IDSs, perhaps, that run in different ways. Now, a lot of what a network IDS is going to use is kind of like a firewall, where's the message from, where's it going to, what's the protocol being used, but perhaps slightly deeper packet inspection than we were expecting in a firewall. So now we're looking at the contents of the TCP packet to work out whether it's a valid protocol in use, or it's an overflow, or it's a known virus signature, and things like this. So as you can tell, this kind of sits somewhere between a firewall and an antivirus. Okay. Now, so it's quite uncommon just to, let's say, install an IDS on this router and call it a day, right? Because your network's going to be much bigger than this if you're a corporation. So what you tend to do is you tend to have some machines that are called sensors or agents, and they will be placed around your network at different key locations, picking up traffic, right? So essentially packet sniffers sitting around your network. And they will have a much more powerful central server that is responsible for actually analysing all this data. So you might imagine that you have a sensor placed at the gateway to A32 to monitor what you guys are up to, right? And then that sends its traffic back to, let's say, Kings Meadow for analysis. And they think, right, as an idea. Now, again, it's unlikely that this is going to start kicking people off the network. I'll give you an example. During the first time I ran the labs a few years ago, there was a massive load of bandwidth suddenly used from A32 at the exact hours of the labs for about the first 3 or 4 weeks. Now, there is no big bandwidth being used in the labs, so I couldn't explain it. I've never worked out what it was. I think there was a group project doing something at the exact same time, coincidentally. But they said all that happened was the intrusion detection system, or the traffic monitoring, flagged up on William Armitage's machine, and he just sent me an email without comment, just a graph of a massive amount of bandwidth at this exact time, and said it, question mark? I just went, don't know, sorry. But yeah, we don't know. If it was you, hey, just keep quiet, you got away with it. So the thing is, so sometimes it's just a case of flag it up, right? Maybe there's something we can do. Just look into it, make sure I haven't done something wrong with the virtual machines that means they're pulling a huge amount of bandwidth that they shouldn't be, but it's probably okay. Right? No one got in any trouble because no one really, as far as we know, had done anything wrong. So, we're going to report to the administrators, logs, alerts to the console, emails, right? The guys in RSG get emailed when we get viruses on our machines. I didn't know this. It happens to me a lot because I download them to see what they look like, and then immediately my computer goes like this, and then they get emails, and then they just sort of knock on my door a few minutes later and go, everything okay in here? Yeah, it's fine. Okay, so they get notified just so they know what's going on the network. So the nice thing about this is we can have multiple sensors to distribute the capture across the network, because the network, as I say, is really a collection of sub-networks, and so you can't see everything all at the same time. Right? But we can centralise the computing overhead. You're going to need quite a powerful machine to run the kind of deep packet inspection that you might need to do for an intrusion detection system, and this helps us do this. All right, so that's all I'm going to say about where you put them and why. Right? How do they work? There's really 3 ways. There's stateful protocol analysis, which is very similar to a firewall, but with statefulness. Then a signature-based detection, very similar to an antivirus. And then anomaly-based, which is build a model of what normal is and try and find the abnormal. All right? And here, again, I'm talking specifically about computers. So, protocol analysis is the idea that we know what a FTP handshake looks like, or a TLS handshake looks like, right? Yes, there's variants of these protocols, but we know that you have a client hello, followed by a server hello, and then a certificate, and so on. So if things start going a bit awry, and we start getting strange responses, maybe we can detect that as something a bit unusual. Right? So we're going to hold detailed information on different protocols that could be used on this network segment, bearing in mind there's going to be some we just don't know about. Right? And we're going to examine for attacks. So, for example, you could say, well, look, why is this user logging in as root? Right? Which you're not going to know necessarily in things like SSH and TLS because it's encrypted, but you would know for something like FTP. Right? Logging in as root on FTP, terrible idea. Right? Very good reason for an IDS to stop that from happening. Right? Why is this command being sent using a 1,000-byte buffer when we know that the maximum payload size for that message is 60 bytes or something like this? Right? Now, I'm just making these up, but the idea is that you've got a set of rules for different protocols, and we know how big they should be. If you start deviating from those, then either, in the best case, you've probably just got a bug or an old client that's out of date, but you could be fishing around to see if its buffer overflow is available or to see what level of software security they've got. Now this is going to be very computationally costly, right? And the idea also is you've got to keep up to date with all the possible versions and all the possible sort of varieties of different protocols. Like TLS has like 5 different handshakes depending on which protocol you choose. And they're all similar but not the same, and you've got to be able to detect all the possible issues with those. Right? So this becomes quite a challenge. Right? But of course, maybe these sell for a lot of money, so you can afford to pay people to do this. I don't know. All right. So a signature base, right, which is nice because it ties into the thing I mentioned on antiviruses, is basically exactly the same thing. But we're talking now about operations, not just binaries. Right? So it's kind of more heuristic based. So we could be talking about things like network, signatures of packets over a network, or the temporality of packets, so how often they're coming, the frequency, things like this. And then if you match a defined signature, which could be like this many packets to this port in this amount of time, or it could be a packet of this size, or anything else, right? Then that's when you start triggering an alarm, or sending an email, or logging it. Okay. Now, the way that most IDSs work is they're going to include some form of attack language. Right? So this is kind of true also of antiviruses. So they're going to have their definition file is going to have a standard format so that you can so that the people that work for that antivirus company can write new definitions as viruses come in. Now, in an IDS, you're going to have some kind of attack language that says, I want you to start logging packets that are coming at a certain frequency on a certain port to a certain destination, and then you can have rules, quite stringent rules, about what gets captured and what doesn't. Right? And hopefully, if your rules are good, you only get stuff that's actually nefarious and don't get anything normal at all. Right? But it's hard to do. Because they have the exact same problems as signature-based antivirus. Right? Now, one thing they can also do is monitor intermediate states. So think of this like stateful packet filtering, where you've seen a certain packet, let's say, and you think that's not suspicious in and of itself, but maybe if the next packet is also a certain thing, then it gets suspicious. Right? So you can have these state transitions. So this is exactly like antivirus, right? They're very computationally efficient. You could theoretically put a signature-based IDS outward-facing on a university network. If you had a powerful server, it could probably do it, like probably. But it's a huge undertaking, but it is computationally efficient. Now, it's always going to spot known attacks. If your attack language is well written, then you're always going to find something that adheres to that attack language. It's always going to miss unknown attacks, because something new is not going to be in its dictionary. It's not going to be flagged. Right, unless it looks sufficiently generic. And you've got to always keep these signature databases up to date. So, for example, you might have a signature that detects valid TLS. Well, when TLS goes to 1.3 or to 1.4, that's going to be out of date. You've got to keep those up to date. Otherwise, old connections are going to start causing alarms or be let through when they shouldn't, and things like this. Okay. So, what would a signature like this look like? Well, let's use an example of Nmap. Because I like Nmap because it's an attack that has a very obvious fingerprint, as it were. Right? So let's imagine that we're here and we're Nmapping a network of some description. Right? And somewhere on this network is also an intrusion detection system. What signs could it look for to see whether someone's performing an Nmap scan? Any ideas? Yes, right. Sequential port access, right? Ping. Lots and lots of ping. Lots and lots of TCP SYN requests without any acknowledgement. Things like this, right? That's exactly right. Okay, large amounts of ICMP, that's ping traffic. Right? Many TCP connections coming from the same place to lots of different destinations. That's very suspicious. No one really does that, right? These connections go into a variety of other computers, not just one. Right, if I go to Amazon, I'm going to set up quite a few TCP connections, probably, to handle different HTTP requests and things. Right? Possibly, anyway. And that's not suspicious. Right? That's totally normal usage. But if I do it to 10 servers at exactly the same time, in fast succession, maybe that's more suspicious. Right? And also, this is going to be going from interesting port numbers to interesting port numbers. So, so we could say, OK, let's write ourselves an attack using my fake attack language that I've written So if a host establishes more than 3 TCP connections to any other different hosts in 5 seconds, then we're going to flag this as a port scan. And we can either block them from the network or we can log it. Right? Now, I just made that up. Right? Is 3 good? Is 5 good? I don't know. That's the problem. Right? If you set these thresholds, at some point someone's going to do that in normal use. If you wanted this to be in your intrusion detection system, you've got to test it. Right? You've got to put this in the wild and see how many TCP connections people are typically sending out just in normal use. Right? When I go on Netflix, how many TCP connections are created and to how many different servers? Right? 'Cause it's important to know what your baseline is. In a way, this comes down to us again trying to find what is normal and working out what's normal and if we've deviated from that. Okay, so this is just an example of a sort of pretend attack script that I could write, right? But there are some actual real ones. So Snort is an intrusion detection system for Linux. It has a very cool logo. And it's an intrusion detection and prevention system. You can use it to prevent things. Typically, it's not used for that, as far as I can tell. So it's open source, which means that the rules that it has in it are written in a standard attack language and are also open source. So, there's a community contributing rules to this sort of big database. So when you install it, it's unlikely, unless you have a very specific use case, that you're going to install your own rules and come up with your own stuff. It's more likely that you would just run the default ones. Okay. So this is an example of its attack language. So roughly speaking, it goes a bit like this. You've got some action, the protocol, so TCP for example, the source IP and port, whether it's coming in or out, the destination IP and port, and then all the other options. Right? Now you can do a lot of stuff in that. I'm just showing you one example just so you can see kind of what it's like. Right? So this is a kind of pretend thing that checks for buffer overflow. So we're going to activate this rule on any TCP packet that comes in from anywhere coming into 121, right, which hypothetically is my SSH server, right, because on port 22. It's going to activate this rule, right, and it's going to flag a message to the admin of possible SSH exploit. Right? And what it's looking for is any content where the byte is equal to 90, /x90. Does anyone remember what that is? It's the Intel no operation instruction. Right? So if it finds any 90s, it thinks that's suspicious, starting from byte 40 up to about 75 more bytes, but the packet's also got to be big. Right? Now I just made those up, right? So I have no idea if that's a real SSH exploit. It's not very important. You get the idea, right? So a very explicit rule, and then when it activates this, which is activated by 1, it's going to log any packet coming into this address for the next 100 packets. Right? So it's not going to kick them off the network because we don't know for sure that it's an attack. All it's going to do is log them and alert the user possible SSH exploit. And then it's up to the user to follow that up or not follow it up, depending on if they want to. So how would you write a rule in Snort to detect Nmap? Right, this is the kind of log you'll see if someone is Nmapping, right, in normal Nmap usage. Right? I'm not going to ask you to look through it. I'm just going to highlight the things that I think are interesting. So the first thing is that the source port is incrementing, right? 3537, 3538, 3940, 41. Right? That's pretty unusual for normal use. If you have a browser or something like that, what it will typically do is generate source ports at random to the destination. Right? Or SSH will connect on port 22 and then jump to a random port and use that for communication. So that's suspicious. Right? Maybe on its own that's not that suspicious, but it's a bit worrying. The next thing is the timings. So these are the times that this was being sent. So 127 and 32 seconds and 464 milliseconds. And this is 464.1, 464.2. So these are thousandths of a second between these messages. Right? That's also quite unusual. Right? That's not uncommon, but you'd be sending them all to the same person. That's a bit, bit unusual. Right? And finally, these are the TCP flags, and these are all SYN packets. Right? Not acknowledgement or SYNAC or FIN or reset or any of the other possible TCP packets. They're all synchronized packets. Right? So you can imagine actually it's not that difficult to write Snort rules that find rudimentary Nmap scans because they're pretty obvious. The problem is that Snort is open source and so is Nmap. Right? So as soon as you write a rule and commit it to Snort's Git, right, the Nmap people read it and go, interesting, okay, we'll just tweak this a bit then. Right, maybe we'll use random sources instead of incrementing sources. Right. So, for example, in Nmap, you can set your timings to be different depending on whether you want to avoid intrusion detection. So for example, you can put Nmap in paranoid mode, which will only send one TCP packet every 5 minutes, right? And your Nmap scan will take about a week. But you will find it and it won't be detected because no intrusion detection system is going to be logging a week's worth of intermittent TCP and finding that, right? Because it's just unreasonable. Right? And also, TCP packets do go out on networks from time to time, right? So you've got different options ranging from paranoid all the way up to insane, right? Now, insane means you don't care if you crash both the host and the person performing the Nmap scan. You're just going to deny the service the hell out of everyone. And then we get a little bit more until sneaky down here is about once every 20 seconds or something like this, right? Now, there are lots of other Nmap intrusion detection system avoidance measures, for example, spoofing IPs. So you can send 3 times the number of Nmap packets to someone, but 2 in every 3 come from spoofed IPs. So it looks like everyone's Nmapping them. And then you can't work out who the real guy was. So it's going to be an arms race. The people who develop Snort are going to be able to see this and go, right then, and then they'll just change the rules, and so on and so forth. Right, which is what I think is quite interesting. I don't know who wins. I don't know. I mean, paranoid, that's hard to find. Right. But also very boring to run. Okay, so let's just finish by talking about anomaly detection. If we don't want to just script some languages specifically and say it's going to look like this, the attack, we don't really know. Right? Then what we want to do is try and use anomaly detection. Now, this has a lot of wide-ranging uses. There's an interesting number file on this about, is it Benford's number or something like that? And that's the idea of if you take a random sampling of numbers, they're more likely to start with a 1. Right? So if you file a tax return with an unnormal amount of the other numbers, then they think it's fraud. Right? That's an intrusion detection system, basically, or a fraud detection system. They're both the same. In my analogy, they're the same. Now, we want to build up a picture of normal usage, and then detect usage that goes above and beyond this, right, basically. And this is always going to be a trade-off between false positives and false negatives, always. Like, you're never going to get it exactly right. So this is an obvious example. We have this normal distribution, and then we have this obvious outlier, right? It's never that simple. Right, I wish it was. So what we want to do is we're going to run a host within a quarantined environment or in its own network on its own and just build up a picture of what it does, the CPU usage, resource, applications, network, over a period of like a week or something like this. And then eventually collect enough training data that we can decide our model for what is normal. So we could use normal sort of mathematical modeling, or we could use machine learning for that. Right? So we don't have to do this online. We could do it by monitoring audit logs. Right? In the first lab, we went through the auth log and saw a lot of connections previously, so we could quite easily build up a picture of what is normal for an authentication log based off that. Right. Now, sometimes this is going to rely on sequences of system calls as well as sort of higher-level things. Right. Researchers suggested that if you group system calls into, let's say, groups of 3, that's quite an interesting. Those sort of triplets are quite an interesting fingerprint for most actions. Yes.
If your machine is intruded upon while you're training, aren't you essentially training to not detect intrusion?
Yes, very good. I was going to mention that. Definitely. Yeah, no, that's exactly, yeah. So you have a huge problem. If you're using machine learning, for example, then you've got to train this, and then you've got a question of when do you retrain it, right? Maybe I train it while I'm writing my dissertation, and then I finish my dissertation, and I uninstall Word, and I install Far Cry instead, and I have a whole different use case, right? And the problem is that I was training the network on the first bit, and it doesn't generalize. And so the problem you've got is that if anything is happening untoward during the training process, you've got a problem. And if you're doing incremental learning, where you're slowly training over time, you could also subtly build in attacks into your training set, right? If they happen slowly enough. That's a huge problem, and it's not solved, right? So, sorry. Okay. So we could use something simple like statistics, right? So this is my probability density function. This is a Gaussian distribution, or bell curve. And I have this hypothesis that for network bandwidth, right, my hypothesis is that this is kind of normal. I don't know, I made that up. Right? My normal network bandwidth has an average of this much, and it comes up and above and below. Right? And my hypothesis is also that maybe when someone gets onto my machine as an intruder, they're going to use extra network bandwidth because, I don't know, they're going to download some viruses or offload my files to the cloud or something. Right? And if that happens, their network bandwidth is going to be here. Now, there's an absolutely massive problem with this. Can anyone see what it is? Yeah. There's a pretty big overlap. Right. So where do I put my threshold to detect an intrusion? Right, disaster. So the obvious case is halfway between the two. If I put it here, and I see network, if I capture network bandwidth for, let's say, 5 minutes, and it comes out here, is that an intrusion or not? And the answer is it's 50-50. That does not help me. Right? So, okay, so I decide to be pretty lenient, and I put my threshold way up here, and only capture this false positives. Great, but I've missed half of the intrusions. Right, and if I put it down here, I get nearly all of the intrusions, but half of my bandwidth, my normal bandwidth, is also an intrusion. Right? So there is no good, using this kind of model, there is no good place to put this threshold. Right? Now, obviously, this is just one parameter. If I had lots and lots of parameters, maybe I could get something going that's not entirely terrible. The other problem is that network behavior doesn't look like a normal distribution. Right, because you're doing different things. It looks something like this, right, where the amount of network bandwidth you use over time is dependent on what you're doing. Right? So this is normal. This is when I'm just sort of getting emails or updates, Windows updates. Right? This is maybe me browsing the web. Right? This is me playing online games. Don't have time for that, but let's imagine I did. And then this is me watching Netflix. Right? And up here is 4K Netflix. Now, if that's the case, you know, and we measure, let's say we measure another 10 minutes of network bandwidth and it comes out as that. Is that normal? I don't know, this looks funny, but I mean, I have used network bandwidth here, so it's difficult to say. Right? This is a very, very hard problem. Right? By the way, I don't have any solutions to this. I'm just telling you how hard it is. Right? So, machine learning can help a little bit. Right? Instead of setting thresholds, what we can do is just pass all of this junk into a neural network or something clever and hope that it comes out as a decision as to whether there's an intruder or not. Now, has anyone done a machine learning course? A few. Right, well, don't worry too much because I'm not going to talk about it, apart from this big picture of a network. The whole point of machine learning, right, is that you're trying to learn a mapping between the inputs and the outputs, right, essentially. And it's quite useful because you don't have to program this mapping yourself. You just give it training examples and it learns that mapping for you. So this is quite well suited to intrusion detection because we can collect very easily a lot of information on different aspects of the sort of things that might be relevant to intrusion. And then we can also collect data on whether or not it was an intrusion. So this is our sort of training data. And then over time, maybe we can train up a network that does this. Right? Now, that's all I'm going to say about machine learning. Now, this is all very well. Collecting the data is a bit of a pain. Right, because we've got to have actual intrusions that also go in the training set, otherwise it's going to be unbalanced. Right, that's a problem. Also, the problem we were just talking about, where if you train this and then something changes in your normal use case, this isn't going to work. Right? This will throw a huge amount of false positives if you change your behaviour. Right? And people change their behaviour all the time. Right? So you've got to collect this over a massive period of time if you want it to be sort of averaged out. Right? And it scales poorly. Right? It doesn't scale because, you know, this network here has 3 inputs and 4 hidden layers and 2 outputs, and you can see all the connections we need to learn to get that to work. Right? Let's imagine you have 200 inputs, 200 input features, because that's how much data you're collecting, hundreds of hidden neurons and outputs. It's going to be a real problem to train this. Right? And running this in real time is also a huge problem. Right? But these kind of systems are deployed on things like Cisco routers, at least to an extent. Right? At least to an extent. And then we've got this problem of normal behaviour can change. So maybe the intruder is already there when you're running the training, or we accidentally miss some attacks while we're training and flag them as normal, and they get learned into the training set. Yes?
So you mentioned some antivirus based machine learning. Would they offload it to the cloud somewhere? Would that use the training itself?
Yes, I think so. I don't think they would. I would hope they wouldn't expect someone's home graphics card, for example, to start churning through. Yeah, they'll collect. What they'll do is they'll use you as one of the sensors to send them usage data, and then they'll use it for training, right? But again, difficult to know whether your usage data is normal or whether it's an intrusion, or, you know, I mean, they can do the best they can, right? I think for a thing like a router where you're just looking at simple packets, maybe it's doable because you've got fewer input features and your problem is maybe slightly easier. For high-level application-level data and application usage, this is very, very difficult. Nevertheless, it's something people are working on, and we shall see now that deep learning is a thing, maybe that will help. Maybe not. Okay, thanks then, I'll see you tomorrow.